All right, so today we're going to look at graphing rational functions. So there's two types of rational functions you guys are going to be graphing. One of them is pretty easy to do because you can do it with transformations. It's one that we've already done. And the problem is not all rational functions, not all fractional expressions can be graphed by just thinking about transformations. So that's the investigation that you guys have been working on so far, is you've been discovering three of the main properties that you need to be able to use to graph rational functions. So I'm going to be using those properties and explaining them, giving you a little bit more as you complete your investigation for this Monday. Okay? So which one of these two functions, f sub 1 or f sub 2, do you guys think you can use transformations on? F sub 1. Why can you use transformations on the first one but not the second one? Because this guy, it's really not clear what the parent function is. It's got x's in two different places. This doesn't come from any basic parent function. So you've got to use some of the things you guys have been investigating to graph it. I'll show you in just a sec. So I'll go through the steps. Hopefully they should mainly make sense from what you guys did with the investigation. Okay. This guy over there, though, has a parent function. What's its parent function that has just been modified?
1 over x.
It's just 1 over x. So let's keep that in mind, that on this guy, we've got a parent function. I guess I'll call it p for parent. That's 1 over x. That's a shape you should already know. And so hence you can just move it around in transformation. So where has this guy been moved? Down 2, I agree. That guy outside's going to move it down 2. What else?
Left 3.
This is inside, so it's going to be opposite. So left 3. And the 4 is multiplied by the whole thing. So what's the multiplication do to stuff? So stretch. And it's not inside on the x, so it's a vertical stretch. You got it. So stretch by 4. The stretch isn't going to make that big of a difference on the graph. It'll, of course, alter all the points the graph goes through, but I don't think it's going to change how it looks a whole lot, okay? So this guy's really easy to graph. You can go ahead and do that. And you'll have some more problems with these in your assignment. All right? So we're going to go left by 3. So I'm going to move the asymptote that was here on the parent function. Left by 3. Let's just remember what that parent function looks like. We should have it memorized by now. So here it is. It's like that, right? There's the 1 over x shape. So I move that asymptote left by 3. And then I've got to move this asymptote down by 2. You want to label them both. Y equals -2. X equals -3. Make sure you have your asymptotes labeled. They're on my quiz or exam. You'll lose points. And then we know it's in quadrants 1 and quadrants 3. The only other thing we have to worry about is this stretch. That's not going to really change it too much. Instead of being real tight in the asymptotes, it's going to vertically stretch it out, which for this shape is a little difficult to think about. But basically, it's just going to like make it pull away from the asymptotes more, rather than being real tight in there in the crosshair. Okay? So this guy's also going to do the same thing. He's not going to be real tight in there following those asymptotes. So there you go. If you've got a transformation graph, it should be real easy. On some of your problems, it's going to ask you for the asymptotes. Just draw it first. Do a real quick sketch. It doesn't have to be super pretty. And you'll have, there's the horizontal asymptote, there's the vertical asymptote. But should you write an asymptote as just like 2 or -2 or 3? No, you've got to specify what kind of line it is. Is it x equals vertical? Is it y equals horizontal? Or is it mx plus b? Some diagonal line. We're not doing those ones now. I skipped those problems out of the book for you. Leave that for another year. Okay? So that's if it's a transformation graph. This guy, you can't do 1 over x because there's like another x on top, okay? So you have to go through a little bit more stuff. Some of that stuff isn't so different, though. So some of your problems are going to just ask for a couple things, like what's the vertical asymptote, what's the horizontal asymptote. Some of your problems are going to ask you to go ahead and graph it. You should not be using your calculator to do that. This should be stuff you can do without your calculator. You can use your calculator to confirm it, of course, but that's about all. I'm going to do it Monday. I was going to, and then I was lazy and didn't get up at 3 like I was supposed to. So. Okay, so where's this guy undefined? At 6. That guy was undefined at -3. What did that lead to on the graph of that guy? An asymptote. It's no different here. If it's undefined at a spot, that's going to be an asymptote. So this guy, from the bottom, you get vertical asymptotes. That's what the bottom tells you. It tells you your vertical asymptotes if you set it to 0. Okay, there could be 1, 2, 3. This one just has one spot where you can make it 0 if you put in 6. So I'm going to go over here at 6 and make a vertical asymptote. There we go. That's like step 1, if you will. Step 2, I want to find intercepts for this guy. So let's find the x and y intercepts. How do you find the x-intercepts, otherwise known as zeros? I think you guys had an investigation on that too. Where did you look for zeros?
All 4.
Anybody figure that out? If you did the investigation and figured it out, then you'd find that zeros come from the top. So you look at the top to figure out where stuff is 0. That's because 0 over anything, doesn't matter what the anything is 0. Unless it's 0, then it's funky. So we'll talk about that in a second, okay? So 0 over anything except 0 is 0. So that means we just need to look at the top and solve for where it's 0. So on this guy, I have an x-intercept, or a 0, at 3. So I'm going to go plot that. I'll plot this guy in red. So 1, 2, 3, look somewhere about right there. Okay, so I've used the top, I've used the bottom. Sometimes, like most of the time, pretty much always on these guys, you have a horizontal asymptote. I'm not going to say always, because there's other kinds of rational functions we study another year. That's not true. But all the ones I gave you guys have horizontal asymptotes too. That was investigation 2. Somebody tell me, looking at this, what my horizontal asymptote will be.
4.
So Akash and Jacob said it's going to be 4. How the heck are they getting 4? Well, here's what you should have discovered in your investigations. Let me give you a little note. So horizontal asymptotes. Here's the rule. There's 2 cases, case 1 and case 2. Case 1 says, if the degree on bottom is bigger. Is that true for this rational function? No, because it's a line on the bottom and a line on the top, so the bottom's not bigger in this case. So what if they're equal? That's the other case. If the degree on top and bottom, so I'm just going to say degrees, are equal. If the degrees are equal, the way you find the horizontal asymptote is you say if the line y equals, because it's horizontal, and you do y equals the ratio of leading coefficients. So in this case, leading coefficient on top is
4.
leading coefficient on bottom is
1.
1. What's 4 over 1?
4.
4. So that's why on this problem we're going to get a horizontal asymptote of 4. So we can graph it. There it is. We're going to do a couple more, so we'll do one with case 1 in just a second. From the investigation, did anybody figure it out though? Besides Akash and Jacob, because I know you guys got it. If the degree on bottom's bigger, what happens? Where's the horizontal asymptote? This is easier even.
Kill him, Akash.
It does happen to be 0 every time. And that has to do with calculus and limits, and as you go to infinity, if the bottom is bigger, it grows a lot faster, so it wipes out the top, and the ratio becomes 0 every time in that case. So we'll leave that discussion for a more advanced class. But for right now, you can just say, hey, it's 0. Done. Okay, so we'll see one like that in a second. So we've got the vertical asymptote. We've got the horizontal asymptote. We've got one point on the graph, the intercept. You could, of course, find the y-intercept. How do you find y-intercepts for stuff, guys? You plug in 0. We could do that. Let's go ahead and do that on this one, okay? So if we plug in 0, let's see what we get. Gone, gone. I get negative 12 over negative 6, which is 2. So I have a y-intercept right here. And in most rational functions, I shouldn't say most, in a lot of them, that's enough. You can totally graph it now. You have everything you need to know. Because the rational function is going to do something, one of 2 things, on each side of any vertical asymptote. So on this side of the vertical asymptote, you guys tell me, is it going to be up in this part or down in this part? Use logic.
Down in that part.
Why is it going to be down in this part? Because we've got the intercepts there. Those are parts of the graph. So what shape is it going to have? Well, it's going to have a rational function shape, which means the asymptotes are going to try to suck it in. That one's going to suck it that way. That one's going to suck it that way. So that's what it looks like over there. Now, same idea. Over here, it's going to either be on top or on bottom. You can, of course, pick a point over here, like 8. It's called a test point, and plug it into the function and see. That's the long way to do it. Use logic. Be Spock. Which one is it, top or bottom?
Top.
I heard top from about 5 people. Why are those people saying top? This is indeed the top. I like that, because Spock. We'll remember that. Okay. Why is it the top? Somebody tell me? Because when we did this over here and set the top to 0, we didn't just find an x-intercept, we found all of the x-intercepts that possibly exist. And if that's all of them and there's not one over here, then it can't go like that. It has to be up there. If you plug in a test point, like if you plugged in like 9 or something out here, it's going to land right there. But you can use logic to do that. If you're not sure, use a test point. Plug it in, see what happens. You'll see what that is what happens. Okay? So there's a couple rational functions. We definitely want to use some more examples. Okay, so looking at 2 more rational functions to graph. What do you guys think? Can we use transformations on either one? Have a look. Is either one related to 1 over x, just 1 over x? So you want to do it that way if you can. It's very fast. They both have multiple x's in them, right? So I don't think you can use transformations. So you got to go through the same process we just did. So let's go ahead and look at this guy. Before you even start doing the process, you should have a reflex when you look at something there. Can somebody? This can be factored, right? So if you see anything that can factor, as you guys are doing your investigation, I saw most of us were factoring first. That's very good. So you should factor when you can. And now let's do the same thing. So we're going to look at the top, we're going to look at the bottom, we're going to find all our asymptotes and so forth. All right, so we'll start assembling the graph over here. All right, so it's going to be undefined and have vertical asymptotes where? At -1 and 1. Because you look at the bottom for places it's undefined, right? That's where you're going to be broken. You're going to be broken on the graph right here at -1 from that guy. And you're going to be broken on the graph right here at 1 from that guy. All right, let's find our zeros. It doesn't really matter which order you do these in, by the way. I mean, like, order doesn't matter. You do them on however you want to get your graph. So zeros, we looked at not where the bottom was 0, but where the top was 0, because then it'd be 0 over stuff, which is still 0. So that's going to happen at 2, right? So I'm going to plot that as an actual point in the graph in red. About right there at about 2. Okay, horizontal asymptote time. So remember, we had 2 cases. There's really 3 cases. We're just not doing one this year because it leads to more stuff. It's either bigger on top, bigger on bottom, or equal in terms of degree. The degree on the bottom squared, on top it's just 1 for a line. So it's bigger on the bottom. That was the default case. You say the horizontal asymptote is at 0, so you go like this. So there's actually a guide right on the axis this time. Okay, you know, I'm going to find my y-intercept because I definitely don't have enough points on this one. We're probably going to have to use some test points besides just Spock logic. So let's find the y-intercept. So I'm going to plug in 0 as my first test point. And you get -2? 0, 0, -2 over -1. Close. 2. Yep. So that's going to be right here. That's helpful. I don't know how I can decide over here, so let's pick another test point over here. What do you guys want to pick? Anything will work. You can pick anything.
6.
6 is over there.
-6.
Okay, you guys want to use -6? 1, 2, 3, 4, 5, 6. Okay, right there, something like that. Make it easy on yourself. I usually pick small values. This is cool though. So -6 minus 2 is -8. -6 squared minus 1 is 36 minus 1 is 35. Now that's some funky fraction. Don't let the funky fraction bother you. All you care about is it negative or positive? It's negative, so is it above or below? Below, and just a teeny bit, right? 8/35. Right there.
Yeah.
Let's see if that's enough points. So this rational function, since there's two asymptotes, has three pieces. One here, one in the middle, and one on the right-hand side. I know where the one in the middle is right now. I don't have to do any more test points. What's it going to look like? Ah, yes, good, very nice. It's going to be like a U shape. I saw some of us drawing a shape because it's going to be up here, down here. It's going to be up there. And I know it's going to be this parabola-ish shape. It's not a parabola because parabolas would go break through those asymptotes. It looks kind of like a parabola, though. How do I know it's not going to go down here like this and follow the asymptotes that way instead? Because of that, that's a good point. But also, are there any x-intercepts in here? No, the only one was there. So it can't do that by logic. Okay, so over here, I can use logic. We've got a test point. You guys tell me, top or bottom? Bottom, if it's going to go through there. There are no more x-intercepts. It can't cross over there. Over here, there was an x-intercept. So note to yourself, I'd make a little note. Can you cross a vertical asymptote ever? So far, we haven't seen it happen, and the answer is no. No vertical asymptote can ever be crossed in math. Can a horizontal asymptote be crossed? Clearly, here's an example of it. So note, vertical asymptotes can't be crossed, ever. But horizontal ones can. Occasionally, let's say. Just for your peace of mind. Okay, so what could this possibly look like if the asymptotes are trying to suck it in? Well, there's two choices. It could either do starting up here, cross, and then get sucked back in. Or it could be like this, cross, and then get sucked back in. I don't know if I can make a decision unless I choose. I think I need one more test point. So let's go over here and make one more test point. So I'm going to pick one more test point. Where should we pick one? I think it's our choice. You can go in there, in there. This is a 2, remember. You guys want to pick 3? Okay, so we'll go and plug in 3. So let's see, if I go 3 minus 2 on top, I get 1. If I go 3 squared, that's 9 minus 1. Oh, that's pretty nice. 1/8. 1/8 is positive, so at 3, it's up here, just barely above. So you guys tell me, does it do this? No, it does this. So it's going to have to be that piece. Follow the asymptote here, cross the asymptote, and get sucked back into it. Try smooth. So there you go. There's a 3-piece rational function. I think you guys saw some 3-piece ones in your investigation, didn't you? Okay. So you can have 3-piece ones, 5-piece ones. I'm probably just giving you 2 and 3-piece ones. Okay. Let's look at another one. I'm going to pause this. Okay. F4. Can you guys tell me what should I do first? Probably. You can break something down. Dalton, tell me, what can I break down? I mean, Dalton. This part, what can this become?
X plus 3 and then x minus 3.
Sweet. Yep. Difference of squares. Good. So before we even start going through our process, this one allows us a nice opportunity. What can you do? Cancel out these chunks. There's multiplication in here, right? So it's okay to cancel. Think of that as a chunk, a quantity. So this simplifies down to x plus 3. Why would you want to do that? Yeah, because now that's a mx plus b line, right? So this guy you can graph much faster. You don't have to go through the asymptote process. It's just a line. So let's graph it as a line. So we've got y equals mx plus b. So we start with
plus 3.
+3 here.
No, y.
It's the y-intercept, right?
Up 1.
And the slope says up 1 over 1 from there, something like that. So that was fast.
But
F sub 4 of x. Yes, there is a but. So if you just graph x plus 3 like in your calculator, you guys did that last investigation too, right? Then of course, it's going to give you a line. It's going to be that line right there that we just drew. If you graph this thing in black on your calculator is of course going to give you a line. Just that line right there, except there will be one thing that's special if you press zoom decimal and have your calculator do it the right way. There's a hole. This line has a hole. Just because you canceled this one, it cancels and makes it simple. But the fact that it had this cancellation in it actually means there's something a little bit subtle. That does cancel out to 1, but the cancellation process, here's how I'd think of it right now before you have calculus and some more advanced math. That cancellation process leaves something behind. Because when you plug in 3, what happens to the part on the bottom?
0.
0. And what happens to the part on the top? So you get something that's 0 over 0. Now, that doesn't have a value of 0 every time. Sometimes it's 0. Sometimes it's infinity. Sometimes it's finite numbers. And you learn to work with that in calculus, this undecidable case of 0 over 0, and figure it out. But on a graph, if you have 0 over 0, what always happens on the graph is that you don't exist on the graph, except it's not an asymptote. Clearly, a line can't have an asymptote. It's a hole. And where is that hole? What causes the problem?
3.
3 is what causes the problem. So at 3, if you trace it up to wherever the function is, you're going to have a hole. And if you graph it the right way with your calculator, you zoom decimal, so when it plays dot to dot, it catches that. You'll see that there's a gap. Okay? So, I'm going to do another example with the other class of another function where you get a hole as well. In fact, should we do a simple one? Let me just do another one with you guys right now. Let's do one more, we have time. So f sub 5 of x. Let's do one that comes out to be transformation. So I'm thinking about this and I'm going to try to make it come out to have transformations possible. So let's see, I'm going to go x squared plus x minus 6 and x plus 3. So if we were to simplify that, you can factor the bottom, right? I tried to make it factorable. Let's see if I did it right. Yeah. And then on top we've got an x plus 3, so what happens? Cancels out. X minus 2 is on the bottom. What's on top?
1.
So it cancels 2, 1. That guy you can do transformations on. It's fast. You can just say it's 1 over x, except this moves it 2 to the right. So here it is. There's 1 over x moved 2 to the right. So there's the graph. You can label it and make it a little prettier, like you want to do in your assignment. Label your asymptote and stuff like that. But there's something special on this.
There's a hole.
There's a hole from that cancellation. Where?
Negative 3.
If you put negative 3 here and here, you get 0 over 0. So at negative 3, there's going to be a little hole.
What about 2?
Okay?
So to show the hole.
2 is the asymptote, Jacob.
Oh yeah, that was a biggie.
So holes come from repeated factors. Asymptotes come from factors on the bottom. Zeros come from factors on the top. So that's a good way to think about it. Yeah, Sam, what's up?
So on the assignment, you want us to just put a little circle this and fill in for the show or no?
Totally. Yeah, that's all you need to do. You don't have to do anything more than that. Make sure it's clear where it's at. That's all.
All right.
Okay. All right. Let me show you guys where some more examples are on the. Okay, so I thought we'd look at 2 more graphs of rational functions. As you can see, neither one is related to the parent function 1 over x. So you can't graph it with transformations, unfortunately. So let's look at our sixth f of x, f sub 6 of x. So let's think about this. First of all, you want to look at it and see if you can break it down at all by factoring. So is there anything that you can factor? And I think there's definitely a bunch of factoring that can be done on each one of these. So the bottom is difference of squares, plus 4 and minus 4. The top, they share an 8. What's left is x squared minus 1. And that's also difference of squares, so we can go plus 1, minus 1 on that guy. So I'm going to go x minus 1 and x plus 1 on that guy because it was x squared minus 1. Okay, so I think that's factored as far as it can go. Look for any repeated factors that'll produce wholes. I don't think there's anything that cancels out here, unfortunately, so we'll just go straight to our process of finding the asymptotes and all that. So what are the vertical asymptotes of this guy? Remember, vertical asymptotes come from the bottom being 0. So the bottom is 0 at 4 and negative 4 on this rational function. Then we also want to set the top to be 0 because that's going to be where we get our x-intercepts, or our zeros. So the top is going to be 0 at 1 from right there and negative 1 from right there. Okay, then we want to think about our horizontal asymptote. So where's that going to be? We've got to think about the degrees, remember? So the degree on the top is 2 since it's a parabola. The degree on the bottom is also 2 since it's a parabola. So if they're equal, remember you look at a ratio of the leading coefficients. The leading coefficient here is 8 and here is 1. So we're going to get an asymptote at y equals 8 over 1 or 8. Okay, let's start graphing it. I think that's enough to start seeing how this looks. So let's see. So we've got a couple horizontal, or excuse me, a couple vertical asymptotes. There's one. And there's one. We've got a horizontal asymptote at 8. And we've got some zeros. We've got one at negative 1. That's actually a point on the function. We've got one at positive 1, another point on the function. So now we want to, remember, use test points and or Spock logic to think about where these pieces of the rational function are going to be. So we've got one here, here, one here, here, and one here, here. So let's see. So since the bottom has 2 x-intercepts in the middle area, I should say, not the bottom, but in the middle region between 4 and negative 4, we have 2 x-intercepts. So I think that that's going to be a pseudo-parabola. It's not quite a parabola, but it's going to go down and follow the asymptotes like that. If you want to find the y-intercept to confirm that, you could very easily. Plug in 0 here, you get negative 8. Plug in 0 here, you get negative 16. What is negative 8 divided by negative 16? I think that's positive 1/2, so mine's a little too high, but you get the idea. All right, so that's that piece. So do I need to plug in more test values to figure out where this rational function goes on the right side of 4 and on the left side of negative 4? I think the answer is no. You could, of course, plug in a value like 5 or 6 out here to see where it lands, but I don't think that's necessary. Just use logic. Logically, the top gives you all the zeros you can possibly have on a rational function or any other type of function if you've got a fractional function. So that means these are the only 2 zeros that exist, which means there cannot be an x-intercept over here, so the function must look like this. That also means there cannot be an x-intercept over here, so the function must look like that on the top over there as well, following the asymptotes. So I think that's it. That's it for that function. You could plot a couple test points to see. Okay, let's look at one final example. So f sub 7 of x, another rational function. So of course, again, you want to start by factoring if possible. So let's go ahead and factor this guy. So the top, oh, I want to change it a little bit too. I wanted to add an x there. So the top, I think, shares an x. So let's pull that out, see what's left. On the bottom, I think they also share an x. And I look at that and I say, hey, that's difference of squares. Let's turn it around to see it more clearly. So I'm not going to change it, I'm just going to reverse the order. So that's x squared minus 25. I think if we turn it around, it'll make that easier to see. Okay, can we do any more factoring? I think the answer is yes. I see some more stuff that I can factor on top. That's a standard trinomial. What is it, 8 times 5 is 40? Yeah, 8 and 5 will give me 3. I go negative 8 and positive 5. All right, so after we've factored the top and bottom, this is what we have so far. I want to look for any factors that are going to be repeated. And I think we've got a couple here. We've got one at positive 5, that's repeated, so that's going to be a whole. And then we've got an x, that's also repeated, so that's going to be a whole. So I'm going to make a note to myself that we have 2 wholes. One of them is going to be at negative 5, and one of them is going to be at 0, or that is 0 over 0. All right, so let's go through and start graphing what is left. So what is left? Let's make that nice and clear. We're going to have x minus 8 over x minus 5. So I think we can find our vertical asymptote first. So if we look at the bottom and set it to 0, we're going to get a vertical asymptote, of course, at 5. If we set the top to 0, we're going to find our 0, or our x-intercept. I think there's only one in this case. It's going to be x equals 8. And our horizontal asymptote. Let's think about which case this is. Is the tree bigger on top, bottom, or are they equal? And I think you can look at the resulting or the original equation to determine that. It's up to you. So here in the resulting one, they're equal, right? Line over line, degree 1 over degree 1. So the coefficients are 1 and 1 in this case, so that means we have an asymptote at y equals 1 over 1, or 1. If we had done it to begin with, you might say, hey, isn't it going to be 1 over negative 25? But those aren't the leading coefficients. The leading coefficient up here is degree 3 over degree 3. Leading coefficient there is 1. Leading coefficient there is 1. See, that's the same answer, 1 over 1. So let's put this together. So we've got an asymptote at 5. We've got a 0 at x equals 8. We've got a horizontal asymptote at 1. And is that enough information to draw it without doing any more? I think the answer is yes. We can use logic here to say it's got to go through this point, so it's going to be on the bottom. And then over here I can use logic to say that it's got to be up here because there are no more x-intercepts. So then I've just got to put my holes in. One at 0 and one at negative 5. So those are the 2 holes in the function. I hope you found this helpful.